In this video, let's examine the convergence of the Bessel function, another example of a power series. So just a quick recap of the last video. To solve the interval and radius of convergence of a power series, what we need to do is start with the ratio test, simplify up until the point where we get it down to x and solve the limit of n. And then set it less than 1, because with the ratio test, if the limit is less than 1, the series converges absolutely. And also, once we know the interval of convergence, we also need to check the boundary points, because the ratio test is inconclusive, specifically in those cases. But let's look at a fresh example. So the Bessel functions, there's Bessel functions of different order, Bessel function order 0, 1, and 2, which the graphs are shown here, which model a lot of vibrations across a circular distribution. So imagine dropping a stone into a pond and watching the ripples progress, or banging on a drum and imagining the patterns that follow. Basically, those functions are kind of complicated. They are much like a trigonometric function. And in a couple classes, we'll talk about how trig functions can actually be represented with power series, as can a lot of interesting functions. A very cool idea that we'll come back to. But Bessel functions are named after the astronomer Frederick Bessel, who discovered these functions when he was working on Kepler's equations for planetary motion, basically examining our solar system and the patterns in which they go around. But basically, he discovered these very specific types of functions, which are very, very useful in engineering, physics, astronomy, and so on. And the reason I'm bringing up this example is, as I was saying, some functions are represented as power series. We sometimes refer to these as non-elementary functions, because this function, you can't represent it using like all the functions we're used to. It's not like it's a sine wave or a cosine wave or e to the x or a polynomial. It's essentially more complicated. And it can't be represented using a closed form solution. It needs to be represented with an infinite series. There is no other way to do it. If you look at it, it sort of resembles a trigonometric wave, a dampened trigonometric function, but again, it's a little bit more complicated. So if we wanted to explore the Bessel function a little bit more, if you look at it again, so for some of you, you might look at this and just immediately shut down and say, okay, I don't like this. There's too much going on in here. But as I was saying in the last couple examples, for a power series, it's good if you look at the first few terms. It will help see what's going on. And while this looks horribly complicated, it's actually it's not that bad. So let's start with n is equal to 0. Whoops. Let me swap my pen. Okay, if we start looking at the first few terms of the Bessel function, if n is equal to 0, well, we're going to have it will be x to the 0, so it'll be constant. We're going to have negative 1 to the 0, which will be 1. We'll have 2 to the 0, which will be 1, and 0 factorial squared, which is actually 1. Basically, the first term is just 1, because all of those terms in that whole thing are just 1 when n is equal to 0. Now, if n is equal to 1, what we'll have is actually not plus, because we'll have negative 1 to the 1. We'll have x squared, so actually the x term will be a square, because as n grows by 1, it's multiplied by 2. And then it will be a positive 1 divided by, the coefficient will be negative 1 divided by 2 to the 2 squared, because n is 1, and n factorial squared. So 1 squared is just 1. So basically that will be 1/4. Anyways, doing all the math, we're going to have is the 1th term is 1/4 minus 1/4 x squared. So now the second term, or technically the third term, but for index of 2, now let's plug that in, we'll go back to positive, because again, we would now have negative 1 squared is positive 1 divided by, and basically we're going to have 2 to the 4th power now, and 2 factorial squared. So 2 to the 4th, I'm just going to write that out, that's 16, and then it would be multiplied by 2 factorial, which is 2 squared, which is 4. So 16 times 4, that's actually just 64. I'll go ahead and write this number out. But essentially, that number is going to get really crazy, because it's a combination of a factorial squared with an exponential. And then our power will be x to the fourth power when n is 2. And so moving on to n is equal to 3, let's just do one more term because you'll see again, we're just trying to explore what a Bessel function looks like. And this is the Bessel function. If you're wondering what the little 0 means, it's just order 0, which is the graph in red. This function, again, basically is given by this particular power series. And so anyways, the term for n is equal to 3 will go back to a -1 on top. And then it'll be 2 to the 6, and then it would be 3 factorial squared. So it'd be 2 to the 6 times 6 squared, and then be x to the 6th power. But again, kind of elaborate as I'm going forward. And then the next term we would have, it would go back to +1 over 2 to the 8th. Then I would have 4 factorial squared, which is 24 squared. And basically, and so on. Basically, you're going to have 1 divided by a very, very large number times x to an even power as that power series continues. And this function models very particular types of circular distributions. Why? Well, that's a much harder question to get into. Something that if you study a lot of differential equations, it will be more apparent why these things are useful. And we're actually going to get into the idea of why these are so helpful on the mathematical side, because they're actually simple to differentiate. But more on that later. Let's not jump ahead to applications and usefulness of power functions. But anyways, our goal is right now just to kind of understand these, see how they work, and figure out again when they converge. So if we want to figure out the interval and radius of convergence of the Bessel function order 0, we need to apply the ratio test. So again, we need to look at the limit as n approaches infinity of the absolute value of an plus 1 divided by an in order to really determine all of this. And so since we're taking the absolute value, -1 to the n will become +1 regardless. And then we're going to have, well, as I usually do, let's just plug it in. We need to start by plugging in n plus 1. Sorry, my arrow got a little bit weird, but as the limit as n approaches infinity of, so if we start with a to the n plus 1, we're going to have 1 over 2 to the 2n plus 2, n plus 1 factorial squared, and then this will be multiplied by x to the 2n plus 2. Also, if you're wondering how I got 2n plus 2, if you plug in n plus 1 in for the index, it'd be 2 times n plus 1 by distributive property. That would give us 2n plus 2 in both of those cases. And this would be all divided by the original formula, which is -1 to the n divided by 2 to the 2n, n factorial squared times x to the 2n. But if you thought our ratio test examples from the last couple classes were bad, this is clearly much, much worse. But as we've seen in all of our examples, these greatly simplify, and these limits generally are solvable without having to, be too terrible. But basically, what I'll do is we'll go ahead and clean this up a little bit and flip and multiply. Also, the absolute value, actually, if you're wondering what happened to the -1, well, again, I already applied the absolute value. Maybe I'll go ahead and, I don't want to do too many different shortcuts at once, but I'll just leave the -1 to the n plus 1 and the -1 to the n there for now. But in the next step, let's apply the absolute value. So the absolute value of a negative will be positive. These are strictly positive as well. And basically, the only place the absolute value will be left over is on the ratio of x. So I'm going to have, again, with cancellation, let's just go ahead and flip and multiply. Sorry, I'm kind of debating about how I want to show you guys this right now. But basically, I would start with the coefficients and flip and multiply those together. So again, after applying the absolute value, what I'm just going to have is 2 to the 2n, n factorial squared divided by 2 to the 2n plus 2 times n plus 1 factorial squared. And then I'm going to have x to the 2n plus 2 divided by x to the 2n. And I'll go ahead and leave the absolute value on x because these ones don't need absolute value out here because, again, those are all strictly positive. and I dumped the -1 to the n because that's just 1 after applying the absolute value. But anyways, a lot of this stuff cancels as they've done in previous examples, because here we have x to the 2n plus 2. That means 2n plus 2x's divided by 2n x's. Well, 2 of those, the x to 2n will cancel with the 2n. The 2 to the 2n will cancel with the 2n right there. And also the n factorials will cancel as well. So actually, if you're wondering how do factorials cancel within a square, well, this actually is probably smarter to just write them out as well. N factorial squared, whoops, is just n factorial times n factorial. So let me rewrite that. So n factorial squared, I'm just going to rewrite it as n factorial and factorial. And then n plus 1 factorial squared is just n plus 1 factorial times n plus 1 factorial. And the cancellation rule for n factorial and n plus 1 factorial is the n factorial will cancel with just factorial in both of those cases. Again, as we've explained before, because n plus 1 factorial is just n factorial times an additional n plus 1. But again, you could just memorize the rules for cancellation. Again, these make sense based on the reasons of expanding exponentials and factorials. But I know algebra, it's just a lot of algebra, and it's not everyone's favorite subject. But anyways, simplifying all of this, let me just rewrite it down now that we have canceled out everything that does cancel as stuff, as what always happens with the ratio test. Well, what I'm left with is 1 divided by 2 squared is 4. Times n plus 1 times n plus 1, or n plus 1 squared. And then it's multiplied by the absolute value of, well, the denominator canceled. That just left me with the absolute value of x squared. And well, technically x squared is going to be strictly positive, whether x is positive or negative, if we're working within the real numbers at least, which we are for the sake of calculus most of the time. But again, as we've done before, the x we can pass through the limit, and again, I'm going to just drop the absolute value because x squared is always positive, and that would just leave me with x squared multiplied by the limit as n approaches infinity. And again, the fourth we could also pass through the limit as well, because that does not involve n, and it would just leave us with the limit 1 over n plus 1 squared. And of course, as n goes to infinity, this will be 0, because 1 over infinity is 0 within a limit. So at the end of the day, we could solve this limit. And actually here, it does not matter what x is, because this limit will always go to 0 regardless of x. And so this is a unique example because actually the Bessel function converges for all values of x. Essentially, since 0 is always less than 1, what that implies is that this series converges absolutely for all values of x. And this is contrary to some of the other examples we looked at. Like in the previous example, this particular power series converged specifically if x was between 0 and 2, including 0. We looked at a previous example where the series did not converge at all, except for if x equals to 0. But there's another option for convergence of a power series, and sometimes a power series can converge regardless of what x is. And actually, if you look at the graph of the Bessel function, notice that it's a continuous function. It converges for all values of x because it's a continuous function. It works for all values of x, and we can kind of see that as we sketch through the math through the ratio test. Basically, what we can conclude is the ratio of these terms, regardless of what x is, x could be a billion, and it will still be a convergent series at the end of the day. That is the value of the ratio test. And so if you're wondering how this differs, well, the limit that we had involving n at the end of the day was 0. It did not actually depend on x. And again, those x's we can all often factor through the limit. And basically this limit was 0 regardless. And whenever you get a limit of 0 from the ratio test, that implies our series converges regardless of x. Where in other cases, the limit sort of summarizing these examples, if your limit goes to 1, then your series converges only in a finite range. If your limit goes to 0, x could be anything, it will converge for all x. And if the limit is infinity, basically those are the 3 kind of things that can happen after solving the ratio test for a power series, then the series does not converge at all. And that's what this final theorem says. We'll talk a little bit more about this in the next video though, because this one's getting a little bit long.